Is begun. Let me go back to my solutions now that I got out of that. And then we'll get underway. Problems. And a 7. Okay, so what we have here in terms of setup, I've got my coordinate grid looks something like this, where on the y-axis at plus or minus a, I'm going to have two charges here. It says 3 identical point charges, so I'm just going to go ahead and label that with Q. And so I've got Q here, I've got Q here, and then I've got Q here, all at y plus or minus a and x equals a. So this distance of a right here, and then this is also a distance of a. Hopefully I drew that somewhat to scale. And we want to know what is the electric potential as a function of position along the x-axis. So I'm going to choose this position right here as x at this point. And what this question is trying to get you to see, as we said maybe a little bit more obscurely, is that the potential at any given point is equal to the sum over potentials that make up this problem. Or specifically, since this is point charges, this would be the sum over I of the I charges here, the 3 charges, divided by their distance from the point P. And so what we want to consider is, okay, what is this distance? We'll call this R1. What is this distance right here? We'll call this R2. And then what is this distance? We'll call it R3. And so what we should get is that the potential at that point is equal to the sum of those. When I sum them up, I can pull out a factor of K. And so I get Q divided by R1 plus Q divided by R2 plus Q divided by R3. Now here's the thing. With electric fields that we talked about before, electric fields were vectors. Electric potential, on the other hand, is a scalar. And so we can add these units directly. The other thing to consider in terms of electric field versus electric potential, the sign of the electric potential, at least for point charges, is determined by the charge. So positive charges mean positive potential, negative charges mean negative potential. And the reason that I'm pointing that out is because if we look at R here, at least in terms of our charge that lies on the x-axis, if we don't set this up correctly, we could get that whatever R looks like, if it ends up being pointing to the left, and we don't account for that sign flip from going from the right-hand side of the charge on the x-axis to the left-hand side, then what we would end up getting is a sign flip in this term right here. So what I'm trying to say is, if I look at R1, what would be the value for R1, bless you, what would be the value for R1 and consequently R2 in this problem? What is R1 and R2 in terms of A and X? Yeah, it's a Pythagorean right triangle, right? This leg right here has side of length A over 2, B, oh, no. I have that written down wrong. This is A, and then this right here is also A. So I've got a side of length A, a side of length X, and so R1 is going to be the square root of A squared plus X squared. Now for this problem, even if X becomes negative, if I go along the negative X axis, then I still get A squared is positive, and no matter what X is, X squared is also going to be positive. I'm taking the square root. So as far as my formulation for R1, and in this case, R2 is concerned, that is an always positive quantity. Now, the reason I'm making such a big deal about that is what is the value, the magnitude of R3, right? What is R3 in terms of its magnitude? Because what tends to happen is, well, if I go from the origin, I go a distance x, but then I have to subtract off this distance a here, and the mistake I see students making is, okay, that's R3 is x minus a, right? But what happens if x is less than a? If x is less than a, what happens? Yeah, it becomes negative. And if I've got a positive charge right here, but a negative radius, I would end up getting a negative potential. But that's not what potential around positive charges look like. What the potential looks like around a positive charge is you get something that looks like this right here. On both sides, all the way around, if you want to imagine that as a revolved line around some axis of symmetry, then I get a positive potential everywhere around that. So what you end up having to do is say that this is the absolute value right here of x minus a. And I just wanted to point that out because when I look at students' homework and you get one like this, what tends to happen is it says, okay, for this point right here on the x-axis, what is the electric potential? And you're like, okay, all of them are positive. I get that, so I'm adding these all together. But then you look at this distance here, and you somehow get negative distance because it's to the left, and you end up inadvertently, accidentally subtracting this off when you should not, and it throws off your answer. And then you get a less than helpful message from Achieve saying, here's what you did wrong. So for this, at least as far as what we're concerned, we have the same Q, and R2 and R1 are the same. So I get K times 2Q divided by the square root of a squared plus x squared plus Q divided by the absolute value of x minus a. And that's it. That's all it's wanting you to solve for in terms of this problem. This would be an Achieve problem that says enter an expression for. Yes? We cannot pull the 2 out from here. Well, I guess we could. If we pulled the 2 out from here, we would also have to consider that the Q. Oh, yeah. Good point. Yes, we could pull the factor of Q out. Let's go ahead and do that. So there's a term of Q in each one of these terms here. So this would be 1 and 2, and this would be KQ. So yes, there's a term of Q on each term. We could pull that out of the parentheses as well. Or square brackets in this case. Yes? Is the next part B missing a clause, like maybe you wanted to say for points on the x-axis? Yeah, it's assuming here that, I think it says use your result here, so that's already assuming that this is on the x-axis as well. The assumptions have to be the same, right, if we're using that result. So the question was, in part A, it doesn't say what's the x component of E along the x-axis. So again, I would try to make that abundantly clear on an exam. But yes, in this case, we're saying on the x-axis for part B. So how would we do that? Part B, how do we find E along the x-axis in the x direction? Oh, here's where your assumption is. It says as a function of x instead of x and y. So how would I find the electric field along the x-axis using my result from part A? Yeah, take the negative derivative. So I've got the minus dv dx. And so if you end up going through this, you get, well, you have to take the chain rule on this, consider that it's raised to power 1/2. And what you end up getting here is that for x equal or x greater than a, let's write it this way, you get, and I'll let you check this out, KQ times x squared, no, excuse me, I missed a term here. 2x times x squared plus a squared raised to power minus 3 halves plus x minus a raised to power minus 2. And this would be for x greater than a. The only thing that changes is if you're looking at x less than a, you get kq times 2x, x squared plus a squared raised to power minus 3 halves. Not plus, but minus x minus a raised to power minus 2. And that would be for x less than a. You think, how do I know to take the two different derivatives there? Well, it's kind of hard to take the derivative of the absolute value of something. Remember that when you take the absolute value, you get one of those nice little cusps in your graph for a sharp turn where the derivative, or the second derivative is, there's a discontinuity there. And so if you look, you end up flipping directions on the graph. Your slope flips, it becomes negative. And so what you could do is consider that for x greater than a, the absolute value of x minus a is equal to x minus a. And for x, running out of room here, for x less than a, the result is for x, absolute value x minus a is equal to a minus x, which is where that negative sign comes in on a result for the electric field. Yes, Kishan?
I got a minus sign on the first term too, like a minus 2x.
Let's see, a minus 2x, because you get you're in the denominator there. Let's see. But then don't forget you've got the negative out front here, right?
Oh, yeah. Okay, that's right.
Yep. And you say, wow, you are so good at calculus, Dr. Waldron. I say, thank you. I used Mathematica. So thank you for complimenting my Mathematica skills. Yeah, thank you. What is A? A is this bottom term here down on the left. This is the answer to part A. A is just the distance up here. The distance, it says that if you look up here, you're at a charge at y equals minus a, y equals plus a, and x equals a. Wahoo! Don't do that during the exam, by the way. That would be very distracting for your neighbors every time you answer a question. Every question, all 150 of you, all 34 questions. It'd be the most exciting and annoying exam ever. Except some of you have to choose Yoshi sounds. Some of you have to choose Luigi, Waluigi, Wario, Peach, Daisy. When I was working for the government, we got 9 new computers, like massive computers in our lab, and so it was tasked with me and one of my coworkers to name the computers. And we went to our supervisor and said, all right, 9 computers. We can either name them after the 9 members of the Fellowship from Lord of the Rings, or we can name them after these 9 Mario characters. And the nice thing was the towers had vanity lights, and so we could set the lights to match whoever we chose. And our government lead said, actually, I've got a 3-year-old daughter who's really big into My Little Pony. I want you to name him after My Little Pony. So it was great hearing all these grown adults sitting in the lab saying, hey, have you moved the data from Pinkie Pie over to Rainbow Dash? And it's like, yeah, it was great. Have fun in your jobs. Find ways to make work fun. That's one way to do it. The other way that I did it was I hid Easter eggs in the code that I wrote. For the government. So they were all Psych references, if you like the TV show Psych. Let's see here. A conducting shell of inner radius B and outer radius C is concentric with a small metal sphere also conducting of radius A less than B. So we've got some sort of setup like so. This is, I want a circle. Nope, not going to give me one. I don't understand why I didn't know that that was a circle. Circle looks like this. There we go. Then you've got an outer shell, looks like this. That's not close at all. And then an inner shell that outer layer of that shell that looks something like this. They look great. Stop laughing. I am totally offended. You just dash all my hopes and dreams of ever getting into art school. There, concentric-ish. This is A, this is B, and this right here is C, right? And then this is a a finite, non-infinitesimally small shell. And on here, we've got charge minus Q, and on this, we've got charge plus Q. And what is the electric potential of the spherical shell? Well, remember that if we can take the derivative of the potential to get the electric field, we can take the path integral of the electric field to get V. So V is going to be equal to the integral, minus integral from A to B. Nope, that's a terrible name since we've already got A1, A and B. Let's say from R1 to R2, radius 1 to radius 2, of E dot dl. And in this case, we said for spherical and or point charges, it's convenient to take our reference from infinity, an infinite radius away. And then we've got R2, well, we're going to go to the radius C here, and this would be ER dr. So it is incumbent upon us, I read that in an article today, and it sounded really, really smart, so I decided I would borrow it. It is incumbent upon us to figure out what the electric field is outside of both of these shells. What is it? Zero, yes. How do you know it's zero? What? Not because it's a conductor. It is zero. Do what? Why is the electric field outside both zero, William? Okay, so he is saying that, okay, since we've done Gauss's law problem, then we expect the total charge on the outer shell to be pulled to the inside, to be attracted to the positive charge on the equal and opposite. That was an invocation of Gauss's law, right? And so Gauss's law states, if I look over this surface outside of my two spheres here, we said that the electric flux, the net electric flux through that green dashed sphere there is going to be proportional to the charge enclosed. And we said that electric flux is equal to electric field times area. What is the net electric flux inside of this green sphere here? Zero, right? I've got just as much plus Q as I have minus Q. And so that means that my net charge enclosed is zero. It means my flux is zero. And if I divide by area on both sides, it means that my electric field outside of that sphere is zero. So we could do a lot of work to do a big, heavy-handed integral that is frustrating to solve, or we can recognize with Gauss's law that the electric field is zero, and you integrate zero from infinity to point C, and you still get that the electric field, the electric potential in part A, the potential of the spherical shell is 0. Okay, so good question. Is it because there is a negative q and a plus q? Yes. If this problem were rearranged in such a way where, let's say that this was also plus q right here, it's not going to let me make that go away. If this was a charge of anything other than minus q, say 0 or plus big Q or a little charge, little q that wasn't the same, then all of the assumptions that we just made would be false. And E sub r instead would come out to be, let's choose this value of little q right here. It would end up being q plus little q over 4 pi epsilon naught r squared. So you would have to integrate that from infinity to c. Good question. That would give you the electric potential there at C. What should end up happening is that you would, in that case, if I'm not mistaken here, you end up getting V would be Q plus Q over 4 pi epsilon naught C is what you would get. So it would be non-zero. That's what you should get for the electric potential if it were not equal and opposite charges. Good question. I was hoping somebody would ask that. Yes, right here. Yeah. Good reiteration. Repetition is the best teacher. Repetition is the best teacher. Never gets old, right? Say that again. Why do we integrate from to C? Okay, so we're trying to figure out, with respect to our reference point, which we said for spherical or point charges, isolated things, we reference with respect to infinity, because if we're going as a function of r squared, when we integrate, it goes to a function of r, and 1 over r at infinity is 0, right? So that's why we choose infinity as our reference point. We integrate to C because we have to consider, again, when we bring in a charge, an additional charge, let's call this charge here Q prime. If we bring this in from infinity along, let's say, the electric field lines that exist, whether they radiate outward, in which case the negative charge would want to follow that inward here, or if the electric field lines radiate inward, then we'd have to be pushing against what it's wanting to do in response to that electric field. But this all is presupposed on the fact of, if we bring a charge in from infinity, how much work are we going to have to do to get it there, right? And so that's what electric potential states, and we're bringing this charge in from infinity to the surface of the outer shell. So that's why we integrate to C. C is the radius of the outer radius of the shell. So we're seeing how much work it would be to bring in a charge from infinity to the outer wall of the shell. It would be the opposite of that, right? You would switch your limits of integration here. But actually, no, let me back that up. What you're saying here is, if we're saying instead of U, if we're trying to find potential energy instead of electric potential, then it does make sense to switch your limits of integration and all of that. What we would have to consider instead is this is the potential from the reference to C. Electric potential is always measured between 2 points, right? So VAB, the electric potential between points A and B, is minus the integral from A to B of E dot dl. So where you're going with this is, okay, what's the voltage, the electric potential between points B and A, right? Well, that would be minus the integral from B to A of E dot dl, or that's just equal to the integral from A to B. By taking the negative, we flip the limits of integration of E dot dl, and that's equal to minus VAB. Does that answer your question? Yeah, and so when we're talking about electric potential here, in this case, it presupposes what I already said, that assumption that we're measuring with reference to infinity, which is why we start from infinity instead of going to infinity. Because we want V at C with respect to infinity here. Come talk to me about it afterwards. Maybe we can clarify it, but just for the sake of time, let's take a look here. What is the electric potential of the sphere, the inner sphere? We now want to know what is the electric potential at the inner sphere. Well, the outer shell, if the electric potential is 0 on the outer wall of the outer shell, then the electric potential of the entire shell is 0 because it's a conductor. Let me say that again. The electric potential of the entire outer shell conductor is 0 because it's 0 at the surface. If we had followed the previous example of what if the charges were not equal and opposite, and we had gotten an electric potential here that was non-zero at the surface, then the entirety of the outer conducting shell would have this electric potential the whole way through it. Okay? So for part B, let me get rid of some of this stuff here. For part B, I want to take the voltage between from B to A, which would be the voltage at R equals A minus the voltage from R equals B. So that's negative integral from B to A of, in this case, the electric field inside the conductor is not 0 because I'm only enclosing one positive charge now. So in this case, E is going to be equal to Q over 4 pi epsilon naught R squared dr, which means that I get the, equals minus minus, get a negative 1, so that's plus Q over 4 pi epsilon naught R, evaluated at B and A. So that's equal to Q over 4 pi epsilon naught A minus Q over 4 pi epsilon naught B. But we want to consider here that what is the electric potential with reference to infinity what is the electric potential at point B? Well, we have to consider here that the electric potential at B is going to be equal to, this right here is, we said is 0. And so we end up having to drop this term right here. And our electric potential is just Q over 4 pi epsilon naught times A. Right? V at R equals B has to be equal to V at R equals C due to the nature of the conductor, and we said that that electric potential was 0. Right? Did I get that right? Let's see here. No. That's what I did wrong. Okay, pause that for a second. I messed up that argument. Let's take a look at this right here. We do get this statement is true right here. But let's say that we get, that means that V at R equals A, there we go, is equal to all of this right here. If we had a non-zero potential at C, so V sub C is equal to this other case that we had right here, you would end up getting that from this integral, V at R equals A minus V at R equals B, but B and C are the same or equal to each other. So we would have to consider both of those together. So the potential at R equals A would then have to be this mess right here. So Q over 4 pi epsilon naught times 1 over A minus 1 over B. Then we would have to add V at R equals C across, so that would be plus Q over 4 pi epsilon naught times C. That would be the correct way to think about it. But since this is all 0 right here, V sub C, our correct answer doesn't have that additional term on the end. It's just got that right there that's in the dotted lines, the dashed lines. Okay? So we have to measure the electric potential between 2 points, right? And so in part B, I was measuring between walls B and A. And so I have to consider that V from B to A is going to be minus V at A minus, V at R equals A minus V at R equals B. It just so happened that since this statement was true, that since we'd already found in part A that the potential at C was 0, then that means the potential at B is 0 because the potential is constant through the walls of a conductor in static equilibrium. Therefore, the result of this integral was V at R equals A is just this integral right here, which we found to be all of this here in the dashed line. Then I followed through and said, okay, if the voltage at C was not 0, if instead it was this right here, if it were not 0, then we would have to add that back across and you would end up getting this result. This would be your secondary result if the charges were not equal and opposite to one another. Any questions on this one? Do I prefer K or 4 pi epsilon naught? If it tends to be Coulomb related, I tend to use K. If it tends to be Gauss's law, I tend to use epsilon naught. I think more in terms of epsilon naught because it's a more fundamental quantity and we use it almost exclusively in electromagnetic theory. But on my exam, if it's a Coulomb-related problem, you'll probably see things in terms of K. If it's a Gauss's problem, you'll probably see it in terms of epsilon naught. Henry? Why did we find the voltage from B to A? So really, implicitly, I was finding the voltage. If I want to know the voltage of the sphere, I was finding the voltage between infinity and A. But I had already found that the voltage from infinity to C was a certain value. And by extension, that means the voltage to B was that same value of 0. So we're measuring still with reference, when we're just talking about, in this term, absolute potential, we're measuring with reference to infinity. But I don't have to do the integral from infinity again because I've already done that part of the path. Okay. Okay. We may try to revisit some of these maybe later because we're missing 3 of them. The solutions are posted on Canvas. But for the sake of time, let's go ahead. I would like to at least talk about capacitors before we're done today. So let's switch gears here and do electric capacitance. The idea with electric capacitance is how can we store charge, right? Or if you're an electrical engineer, it's basically like a really dangerous battery, right? One that you can short out and cause booms to happen. That's the long and short of it if you're not an electrical engineer. If you come across a capacitor, make sure that it's drained of charge. Otherwise, bad things could happen. Do what? Yeah, Practical Guides to Living with Dr. Waldron. How not to die in an electrical lab. All right. A capacitor is generally designed with 2 conductors, one with charge plus Q and the other with charge minus Q, so equal and opposite charges. The corresponding capacitance is then defined as the magnitude of the charge it can store on its 2 sides divided by how much voltage it takes to store that charge in the first place. So you think of a nanofarad capacitor. A nanofarad capacitor would be one that would store per volt nanocoulombs of charge. A microfarad capacitor would store microcoulombs of charge per volt added to it. More voltage that you put on across the plates of the capacitor means more charge that you're storing on the capacitor. Or for a given capacitor, one way you can think of it is if you measure a certain amount of charge on it, there has to be a certain potential across that capacitor to have that charge existing there in the first place. At least in terms of static equilibrium. We'll get into a steady state drain and buildup of charge either by the end of today or on Thursday. But capacitance is charge per volt. How much charge is stored on the capacitor per volt across the capacitor, Maggie? Okay, good question. I think on my next slide here, we have the units of capacitance are known as a farad. A farad, a 1 farad capacitor would be an insanely high amount of capacitance per volt. It would be incredibly dangerous. Don't mess around with even microfarad capacitors. That's still a lot of volt. But 1 farad is equivalent to 1 coulomb per volt. And if you go in the lab, you'll see picofarad to microfarad capacitors on average if you just look at the wall. I don't think at Harding we had any millifarad capacitors. I've seen a few though, but we didn't have any. I don't want to mess with them. You have? What's the largest capacitor you've worked with? Yeah, that's right. The CRTs, right? Yeah, so just like today, people like to take apart microwaves and used the transformers. You also had great capacitors inside CRTs. I don't recommend either of those things. I can't condone that as a professor, but people do it. Moving right along. Self-capacitance is defined as the ratio of the charge stored on an isolated conductor with respect or versus its potential. That is, with respect to infinity. Since it's isolated, it's best to just think of, okay, what's the potential at infinity? It's 0. So consider a spherical conductor, for example. We showed that the electric potential is going to be kq over big R, where big R is the radius. Therefore, the capacitance is going to be 4 pi epsilon naught times R. It has a certain amount of expected capacitance when it is just alone in the universe. You will have non-isolated conductors. Right. So Maggie's question is, what happens, let's say some problem says you have a sphere, and then you've got a spherical conducting shell around the outside of it, right? What's the capacitance of that system, it would say? And it turns out you have to consider that electric potential we just worked with the q over 4 pi epsilon naught integral from 1 over a to minus b or whatever. Yeah, all of that. That would be the potential. You'd have to consider how much charge. Those problems get really complicated to solve. And so what happens is, at least at this level in your physics classes, you will get, in your book, it gives you standard capacitances of standard geometries. Cylindrical capacitors, for example, or spherical capacitors. The one that we're going to most often work with is a parallel plate capacitor, just to work with the idea of what we're comfortable with. And you'll notice that when you take Q and V, what tends to happen is that Q and V divide out. You'll notice that the final capacitance here for self-capacitance has nothing to do with what Q and V are. It has everything to do with what the geometry is, how big it is. Same thing will be true about all the capacitors we talk about. It has everything to do with their geometry. A sphere has a capacitance of 1 microfarad, an isolated sphere, and carries a charge of 20 microcoulombs. If the charge is increased to 60 microcoulombs, what is the sphere's new capacitance? All right, so it is still equal to 1 microfarad. We said just now that the capacitance depends on the geometry, not how much charge is stored on it. Because what happens if I increase the charge on it by a factor of 3, what had to have happened for that to occur? I would have also had to increase the voltage by a factor of 3. Well, if I have Q up by a factor of 3 divided by V up by a factor of 3, the factor of 3 divides out, the capacitance stays the same. It's not until I make that thing bigger or smaller that you end up changing the capacitance. That is a general rule, yes. Whether it's an isolated object or a system. The capacitance is based on the geometry, based on the physical specifications of it, not how much charge or voltage you put across it. In fact, according to this slide, capacitance is derived from sizes and shapes. Implicitly, what that's saying, too, is not from how much charge or voltage you have on or across it. Yeah, not from charge on it or voltage across it. Any capacitors that don't work like that? So what happens, some of you may know the answer to this. You could start entering a sort of nonlinear range on a capacitor where you keep increasing the voltage, but you notice that the capacitance, the charge doesn't ramp up along with it linearly. So every volt that you add, you don't get an additional X amount of charge because you get the repulsive forces over it. And so all of your capacitors are going to have tolerances on them about how much voltage you can put across them. Outside of that, you might start entering a nonlinear, and so the capacitance would drop per volt. But usually what happens before that is something called dielectric breakdown. So if you've ever seen, you crawl in bed at night, and you got your wool socks on or whatever, you get the static electricity, and because the lights are off, you can actually see that static electricity. Something similar to that occurs. You get an arc of charge across the plates of that capacitor, and it gets back into within its tolerances if it doesn't melt, explode, or otherwise, something along those lines. But in terms of what we're going to be doing here, we're going to assume that we're working within tolerances. So this rule is true, that the capacitance is constant as a function of the size and shape, not as a function of voltage, that it's completely linear, charge to volt. Okay, find the radius of an isolated spherical conductor that has a capacitance of 1 farad. What does it have to be 1 farad? Remember, epsilon naught is 8.85 times 10 to the minus 12 farads per meter. So if I take that equation, the capacitance of a spherical capacitor, an isolated spherical capacitor, is equal to 4 pi epsilon naught times R. So I've got 1 farad divided by 1 over 4 pi epsilon naught. That gives me an R of 9 times 10 to the 9 meters. Does anybody have any idea? Can you give us an idea of scale of 9 times 10 to the 9 meters? I mean, we're talking here about the orbital radius of the Earth around the sun. That's how big your conducting shell would have to be to have a 1. So the point is, to store lots of charge, you need a lot of place to put that charge. So here's a question for you. I go back a slide here. These right here, if you're not familiar with them, these are a certain type of capacitor that you could have on something like a PCB. That is not, as far as I'm concerned, the size of the orbital radius of the Earth, but that's still probably, I can't tell in the picture, but microfarad conductor, according to that equation, if I had said microfarad, that would have been 10 to the 3 meters, 9 times 10 to the 3 meters, so almost 10 to the 4 meters, 10,000 meters. That's not 10,000 meters across. How in the world do they store or have such a high capacitance in such a low space? Does anybody know, like electrical engineers? What? Well, you can add things in series or parallel to increase or decrease the local capacitance. So you put a dielectric, something like plastic or ceramic, in between the walls there. The other thing, too, is it's applied origami, more or less, right? You can take a very large size and fold it over top one another, and you expose a large surface area. And so in a lot of these type capacitors, you end up having that it's 2 helixes that are wound up right atop one another. So over a tiny amount of volume, you can have a large amount of exposed surface area, allowing you to store a lot of charge in a very, very tiny place. It's just, I give engineers a hard time, I know that, but this is an engineering marvel to be able to do something like that. I think it's really, really fascinating. So let's talk about a parallel plate capacitor. That's what we're going to use the most in this class. We take two flat conducting plates of equal area A and separation distance D. We then place equal and opposite charges Q on the plates. And from last chapter, we expect that the electric field be equal to sigma over epsilon naught, or that's Q divided by epsilon naught times A. You say, wait a second, what happened to the factor of 2 in there? You told me it was Q over 2A epsilon naught. What happened to the factor of 2? What? They're parallel and there's two of them. Yes, we said that the electric field off of a nearly infinitely sized sheet of charge, which the parallel plate capacitors, the plates might as well be infinite for how close you have to have the plates together to be. And we said that the electric field was constant between, or coming off of those large plates, right? Well, it's a factor of, if you've got plus 2 here, it's going to be a factor of Q over 2 epsilon naught to the right, pointing away from the left plate. And then you've got a factor of minus Q over 2 epsilon naught. That's going to be pulling to the right because electric field lines point towards negative charge. Those are two vectors added together in the same direction. So those factors of 2 add out, and you get the electric field, assuming the plates are close enough together, are going to be parallel, perpendicular to the face of the plates, and you get that they are going to not bow outward. Now you can see here that this is a physical example of a parallel plate capacitor, and you see that the electric field is very much not constant, especially as you get towards the outer edges. So out here, you get what's called fringing. The electric field bows outward because you get a slightly higher collection of charge out here on the outer portions of the conducting plates. So you get some fringing. In this class, we're always going to assume that those plates are close enough together that any fringing effects are going to be negligible and you don't end up changing the capacitance of your system. So we said that between the plates, the corresponding potential is going to be E times D. How did I come up with that? Electric potential is E times D. William? What? Yeah. So the field is constant between the plates of the capacitor, and then you integrate from one wall to the other. One wall to the other is a distance d. When you integrate over a constant, you just pull that constant out and you multiply by what your limits of integration are, basically, or the difference between them, and you get E times D, the distance between the plates. Yes, sir? Why is it not negative? Because we're just talking about magnitudes here. The capacitance is just in terms of magnitudes of charge and potentials. Ultimately, what I'm trying to get to is once you figure out what E and V are, this is all presupposed by the fact that it's a charge Q across the plates. With a charge Q being across the plates, the charge divides out, and you get for a parallel plate capacitor, the capacitance is epsilon naught A over D. Y'all have a great day. I will see you on Thursday.